Ding. All right, so let's take a look and try to get a general idea for the shape of this basic exponential function, y equals 2 to the x. Again, the variable is in the exponent position. That's a little new for us. That's what makes us an exponential function. So we're just going to pick some different numbers for x. So maybe like -2, -1, 0, 1, 2, 3, 4. I guess might as well go to 5. And let's just see what we get when we plug them in to that. Now, some of these are pretty easy. Let's do the easy ones first. For example, like down here, 2 to the first power, right? If I just plug in that x value in that exponent, well, 2 to the first power is just going to be a 2. And then these other ones are pretty easy, right? 2 to the second power, that's just 2 times 2. That's a 4. 2 to the third, you're basically just multiplying by 2 every time, aren't you? Just like doubling it over and over and over again. So this would be 8, 16, and 32. But what about when you go backwards to 0 and negative? If you remember one of those exponent properties from first semester and from Algebra 1, anything raised to the 0 power always equals what number? It equals 1, actually. And here's a good way to think about it. All these powers, like 1, 2, 3, 4, you notice how we multiplied by 2 every time? Because that's the base. Think about it. What if you go backwards? What if you start at 2 to the 5th down at the bottom here? Each time you decrease the exponent by 1, see how we're like dividing by 2 every time? 32 to 16 to 8 to 4 to 2. Well, what's 2 divided by 2? It's 1. So 2 to the 0 power, anything to the 0 power, it turns out, actually equals 1. And what if you go back even further, 2 to the -1? Well, if you recall one of our properties of exponents, if you ever have a negative exponent and you want to get rid of it, you just flip the side of the fraction that it's on. So 2 to the -1 is the same as 1 over 2 to the +1. And that as a fraction, isn't that just 1/2? 1 over 2? So we'd write 1/2. And look, that also does fit our pattern by dividing by 2 every time, isn't it? Like 2 divided by 2 is 1. Isn't 1 divided by 2 1/2? And what do you get when you divide 1/2 in half? Yeah, half of a half is just 1/4. And so 2 to the -2 is actually 1/4. And if I keep on going more and more negative to the -3, -4, -5, it's going to be a smaller and smaller fraction that's going to get really, really close to what number? To 0. Yeah, it's getting closer and closer to 0 every time. So let's plot these on our axis. So at -2, 1/4, that's like just barely above the x-axis. -1, 1/2. All right, 1/2, that's right in the middle. 0, 1. It's actually going to be our y-intercept, right, because it's on the y-axis. Then I go to 1, 2, 2, 4, 3, 8, 4, 16. Do we have 16 on here? Yeah. 4, 16, and then we can't see it anymore, right? 32 is way off the graph. So if we were to connect these dots, we're going to get something that looks like this. Have you ever heard about something that grows exponentially, like that phrase before? It means it grows really, really quickly. And if we look at this graph, can you see how fast this actually grows? Think about how steep it gets in just a few numbers. So back over here, like when I'm at like the negative numbers, is my graph jumping up vertically very high each new number? Like from -2 to -1, it's a very small jump, right? Or from -1 to 0, it's also a pretty small jump. You know, I'm only going up like this much, you know, not even that much, half of that. But when I'm going from 3 to 4, which isn't that far away, right? That's just a few more numbers away. Look how big the jump is from 3 to 4. Boom, that's huge. That's way bigger than how high I was moving just a few numbers ago on the x-axis. And it's going to keep on getting bigger, right, by doubling every time. That's a massive increase. That's called an exponential change or an exponential growth, meaning it grows super duper quickly. much quicker than just a line that's growing by the same amount every time, right? Up 2 over 1, up 2 over 1. Here I'm going, over 1, up 2, then over 1, up 4, over 1, up 32. It's insane how fast this grows, this exponential growth. Now, on the low end, there's also something unique that happens. Let me get rid of this. I drew this part of my graph kind of right on the x-axis almost. I didn't draw it like down below. It's not going below that axis. It's staying right on there. The reason being is if I look at these two values up here, as I mentioned before, if I go more and more negative, which you can think about that like going to the left on the x-axis, right? You're getting more and more negative. As that exponent gets more and more negative, the y value just becomes closer and closer to 0. Do you think it ever will actually reach the number 0? It actually won't. Because here's what's going on. If we're always dividing by 2, imagine if I'm trying to walk to that wall over there, and I can only move half the distance between me and the wall. All right, so between me and the wall right now, I'm going to go halfway there. So I'm right here. Now I'm going to move again, but I can only go half the distance. I'm getting closer, but I'm still halfway there. I'm going to move half that distance, then half that distance, then half that distance. I'm always moving half the distance. Eventually, I'm going to be moving a super tiny amount, right? Like it's barely going to be there. But am I ever going to move all the way to the wall, technically? Not really. I'm always going just half of that amount. I never will really reach it, like on the microscopic level, right? We're talking super duper tiny. But I'm still never going to make it all the way to that wall. I'm only going half the distance. And so this line at 0, my graph is going to get very, very close to, but never actually reach. So we're going to learn about this. It's a special line called an asymptote, and we're going to learn about that in this unit. So that's our graph. Piece of cake, right? I know it's weird, it's different. We'll have fun. So exponential functions. As we graph this, there's going to be 3 main points that we want you to kind of plot. So again, this target is just on graphing these functions. So I'm going to give you a different type of a function with an exponent, and you're going to have to plot it. All right, so what are the key things that we need to keep in mind? First, there's this horizontal asymptote. So that's that line I just showed you right at the end. In this first basic example, it was the x-axis. It won't always be there. It could be up higher. It could be down lower. It can move around. Just like a parabola could move all the way around the coordinate plane, right? So can one of these functions. And so it's an invisible line, and that's asymptote. So this is a new term for you. You might want to box it up, put a note or something. We're going to be seeing more and more asymptotes as the year goes on, and definitely next year in future classes. An asymptote is an invisible line that a graph approaches, meaning it's going to get closer and closer and closer to, but it will never actually reach that line. And so even though it looks like it's on top of it, if you zoomed in super duper close, it actually is still a little bit away from it. So you're going to have the asymptote and then 2 points. We're going to have 2 points to plot to dictate that curve away from it. I just call it first point, second point. It's not like official mathematical terms. It's just how it kind of helps me to graph it. And so there's always 1 point that is just above the asymptote, or if it's a negative graph, it'll be flipped upside down. There'll be 1 point below it. The second point, just go 1 point to the right of that first point, and that'll be like your next one, and that'll kind of dictate how steep that curve is going to get for your exponential graph. So these are the 3 things I'm going to want you to kind of focus on when I ask you to graph one of these. Just like for the parabola, you'd graph the vertex and then a couple other points, mirror them and draw on the curve. This is what I want you to focus on for drawing one of these graphs. So let's take a look at it here. This is the same function that we started our lesson with. And you can see that there's the horizontal asymptote. That should always be the first thing you draw, because that's a guideline that tells you basically like how high or how low your your function is going to be, your graph, like where it starts. It's going to start on that asymptote and then grow from there. And then 2 points. Our first point is always going to be at 1 point above the asymptote. Notice that from the asymptote, there's no other like intersection point. I don't even know what I'm drawing. Like the first number that it reaches is right here. Like there's nothing between the 0 and the 1. Like the 1, that's the first time it actually hits a non-fraction number, I guess you could say. And the second point for this one, so if this is at 0, then I'm going to go to the right 1. And where's this next point? And that second point is going to dictate the steepness of it. If that second point is like way up here, then that's going to be a much, much steeper exponential growth. And so those are the 2 points that we want. The first one's always going to be just one spot above your asymptote every time. All right, so this is always going to be just up 1. It's that second point that's going to vary based on different numbers or coefficients or stuff that we add into the function. And so then after you draw the asymptote, first point, second point, then just draw the curve. And that's going to be it. Seems easy enough, right? Yes. We'll see. I hope so. So when we graph this, we can treat it just like a parent function. We did this for absolute value graphs. We did this for quadratic graphs, for the parabolas. And so we're going to do the same thing, where we kind of analyze the equation and look at different numbers in different places. Now, we've got 1, 2, 3, 4. We have 4 different numbers that can be in our function, in our equation, right? And then there's the x, of course, the variable that we need. Based on what these numbers are, we'll determine where the graph is located on the coordinate plane. Some of these letters are familiar. For example, look at A. A is the vertical stretch or compression. Hasn't it always been the vertical stretch or compression on all the graphs we've done so far this year? Same thing, right? If it's a number bigger than 1, it's going to be a vertical stretch. If it's like a fraction, a number less than 1, it'll be a compression. It's like 1/2 of the original height. Or if it's like a 3, it'll be 3 times the original height for that vertical stretch. This one's a little different. We've never had like a base before. And so based on what the base is, we'll also determine the steepness of it. The example we did, the base was a 2. And so it doubled every time. If the base were a 3, then each number would triple every time. If the base were 5, it would be multiplied by 5 every time. That's all that means. And then h and k, we've seen things like h and k before. And h is the horizontal shift, how far left and right. Now notice, just like we've always seen before, for example, like vertex form of a quadratic or with our absolute value functions, x minus h is in parentheses. So for example, if we had x minus 2 in parentheses, like with whatever our base was, that x minus 2, would that be, so a horizontal shift is left and right. Do you think that's minus 2? Is that going to be 2 units to the right or 2 units to the left? Based on what you remember from throughout this whole year. Does minus 2 mean it's going to go to the right or to the left? What do you think? Why do you think it's to the right, Frank? It's opposite. Yeah. Hasn't it always been the opposite this entire year? Whatever's in parentheses, right? X minus 2 actually means it's going to go to the right 2, not to the left. You flip the sign just for what's in parentheses. And then again, I always keep it straight because it's got an X with it. It's the number grouped with the X, and X means horizontal, right? Left and right. That's your horizontal. And then K, this is your vertical shift, and that was true just for our quadratics in vertex form. That number at the end being added or subtracted, you don't need to flip the sign either. If this said plus 4, then asymptote would be raised up 4 units. It's extremely straightforward. Same thing as our quadratic functions in vertex form and our absolute value functions from unit 1 way back in September. Oh man, remember those days? Good times. No one liked, okay. So this is all stuff that you have seen before to some degree. And so just to kind of illustrate, let me zoom back a little. The difference between two functions, there's one, I got the red line and the blue line on the right. And they both look the same general shape, don't they? Starts out like kind of flat and then starts going upwards really quickly. That is your general exponential growth type of a function. Now, if I compare these two, the base is whatever number is being raised to the exponent. On the right, is the base going to be the 3 or the 2? Which one of those is the base? Why do you think the 2, Vegas? Perfect. Yeah, that's what I wanted you to take away. This 2 is the base because it actually has that exponent right there. The base is being raised to a power. That 3 doesn't have like an x in the exponent spot or whatever. So that 3 is what we would call A, our vertical stretch. It's 3 times taller. And then the -1 and the +2. So the +2 is a vertical shift. And look at where this horizontal asymptote is. See how it just crosses through where y equals 2, right? It was raised up 2 units. And then the -1 means we're shifted 1 unit. And then 3 is 3 times as big. So instead of going up 1, it's going to go up 3 times. And so that first point is actually 3 times above the asymptote. So this is just a brief illustration. I'm going to break it down in the future slides as well. So that's your first point. All right, and then the second point you can see is right there, and I'll tell you how to actually calculate those from the equation. Then you would draw in the curve. So you can see they are similar, whereas here is your first point and your second point, and then your asymptote. So they have these similar components. That's what we're going to identify from the graph. Now, if we have different bases, this is 3 to the x, that one's 4 to the x. So now the base isn't a 2, it's a 3 or a 4. Do those graphs look pretty similar? For sure, they definitely do. Let me zoom in a little for you. If we get even closer, so first, what do these both have in common? How about their asymptotes? Do they have the same asymptote? Yeah, it's that x-axis, isn't it? For both of these. Same exact line. So, doesn't matter what the base is, it's going to start on that x-axis. How about the first point? Do these both have the exact same first point at 0, 1? Yeah, it doesn't matter if it's 3 to the x or 4 to the x. The first point on these parent functions, on the basic version of these, without adding or subtracting or multiplying stuff, is still at 0, 1. The only difference for them is the second point. So over on the graph here, 3 to the x, the second point is at 3. Whereas the second point at 4 to the x is at 4. Do we see a connection there? So this over here was the graph 3 to the x. This graph here is 4 to the x. So whatever the base is, that dictates where the second point is going to be. It's kind of nice. And that's the only difference with different bases. This isn't so bad, right? We're doing okay so far? We're awfully quiet and sleepy, I think. How much time do we have? Oh, plenty. Let me zoom back a little. So if we have a negative sign, This is also something that we've seen before with our quadratics and our absolute values. If you have a negative out in front of the function, all it does is flip it upside down. And so I even add some notes here. This is negative 2 to the x. You can see, check it out, it's the exact same horizontal asymptote right on the x-axis. It's just now the first and second point, instead of being like above, it's just going to be below because it's upside down. First point is at 0, -1, right? Instead of going up 1, it's down at -1 now. The second point is at 2, which again, check out the base. The base is 2. If the base were 3, that second point would be down at -3. So whatever the base is, that's what that second point, where it's going to be located. How far, I guess, away from the asymptote. Okay, so a negative just flips it, just like it has been in all our other functions so far. So what about when I give you a graph with all these different changes? How do I identify exactly what's going to happen? Now you can think about this, how this is going to shift and change those points and move it around. But I also, on this slide, I just kind of want to show you the shortcuts, like little mini formulas to calculate the exact points, which you can use, you don't have to, but it's just another way to kind of help you understand how you would graph these. So I always start off when I have a function like this. I'm like, all right, where do I even start to graph this? And your starting point every time will be that asymptote, that horizontal asymptote. That's always your starting point because your graph is always going to start on that line and then curve up, or if it's negative, it'll curve down. And the easy thing is that horizontal asymptote is always just going to be k, which is just the number after the exponential part of the function that's being added or subtracted. If it's a positive 3, that means it's going to be shifted up 3. So the horizontal asymptote is at y equals positive 3. So I'd go up 3 units, 1, 2, 3, and draw a dashed line through 3 on the y-axis. And that's going to be my horizontal asymptote, my starting line when I draw on the actual curve. Now your first point and second point, I do want to make something clear. I want to stress something, is that these are points, so they need to be an x and a y, right? I need 2 points for an actual coordinate. And your first point is always going to be at h. So remember that horizontal shift, that's going to move it to the left or the right, but you flip the sign because it's x minus whatever h is. Since x is subtracting a 1, that means 1 is h. 1, comma, you flip the sign for h. And then that first point is normally 1 unit above, unless there is an a, which is a vertical stretch. So normally that first point is just 1 unit above that horizontal asymptote. Remember 0, 1, there's always that intercept at 1. But if it's been multiplied by some number, it's going to be 2 times 1, twice that big. So it's 2 units above whatever that horizontal asymptote is. And our horizontal asymptote was at 3. So think about it like this. I already went up 3 units. And then this 2 says my first point is going to be not 1 unit above it, but 2 units above that. And so you add those together, a plus k, and you get 5. And that's because these two numbers are basically your vertical components. The first number is your vertical stretch. The second, that last number, is your vertical translation, your vertical shift. So you add those two vertical numbers together. And finally, that second point that you need to plot to get the true curvature of that exponential function. This second point is always going to be just 1 unit to the right of the first point. So if my first point is at 1, the next point will be 2. You just go to the right 1 unit. Okay, every time. You're just going, what's the next point over? As if you're doing a T-chart. But now the second point, we have to take the base into account. And so it's not just this first 2 plus 3, but it's 2 times 2 plus 3. Because you're multiplying it by that base. Because remember, that second point was always that base units up. If the base was 2, it was 2 units up. If the base was 3, it was 3 units up. But A stretches it. So normally it was 2 units up, but this is twice that. So that'd be 4 units up from the x-axis. Then you just have to add in, well, what about that vertical shift? Oh, yeah, we started 3 units above it. So that's going to be 4 plus 3 to give us 7. Lots of math going on here, I know. Lots of things to confuse and mix up. This is something that you just practice enough and you'll get it. So that's the idea. Once you've got those 3 things, then we graph it. Graph the asymptote, first point, second point, draw in the curve. So let's try, before graphing it, let's just try listing those 3 critical properties for this exponential function. Okay, let's practice that. First thing I want always is the horizontal asymptote. That's the easiest to identify. That's always just the number that's being added or subtracted at the end. What's that number in this case? A -1. Yeah, you just look back here. Whatever's being added or subtracted, that's our horizontal asymptote. And it's a line, so write it as y equals to indicate that it's a horizontal line. It's not just a point, it's not just a number, it's an entire line at -1. So you drop down 1 unit below the x-axis. The first point, where is this located? So this is a point, meaning it's going to be an x and a y. I need my coordinates to plot this point on the graph. I look at the x, and I check, hey, is there anything being added or subtracted to this x? If there is, you would flip that sign. But in this case, since it's not like an x plus something or an x minus something, what number do I use for that x coordinate? If there's no number there, what number should we use? If there was a 1, it would actually say like an x minus 1 or an x plus 1. But if there's no number, what number represents nothing? A 0. It's like an x plus 0 would just be an x. So this first point is at 0. And then the y coordinate, you take the number in front of the base and you add it with that vertical shift. So what is the number in front of the base? So 4, see how 4 actually has the exponent? So 4 is the base. We want the number in front of the 4. Yeah, this is tricky, right? What number is in front of that 4? A -1. Yes, yes, yes. This is actually like a -1. Here, let me rewrite this. This is like -1 times 4 to the x minus 1. So that first point, -1 minus 1, is -2. Then we need our second point, which is also going to be a coordinate. And every time for your second point, look at the x-coordinate of that first point and just jump over 1 number. So we were at 0 the first time, now we go to 1. And to figure this coordinate out, you multiply those 2 together, which is nice because they are being multiplied, and then add this last number, or subtract if it's negative. So that's -4 minus 1 is -5. Plot those points, draw on the curve. All right, you've got an easy delta math tonight to practice this, and we're going to do some more of it on Friday. But definitely, you've got to get that delta math done before Fridays to make the lesson easier. Alex, did you want this sheet? Yeah. Good luck, everybody.
Mr. Wojcik,
Yeah, what's up,
I
Julie?
have a question. Do you know when the next hour ends? 'Cause